amplifier. Yes. So this is the diagram of your current shunt feedback amplifier. Okay. So see, the current shunt feedback amplifier consists of two transistors. It's a two-stage feedback amplifier. Okay. The Part-3 amplifiers are with a single transistor, but the current shunt feedback amplifier is with the two transistors. Okay. Yes, I'll explain that reason first. See here. Suppose if the output is at this point, okay, but it is common emitter configuration, common emitter amplifier, you know it. If the output is at this point, suppose if you connect the feedback like this, you know, it becomes voltage shunt. If you have any node here, it becomes the shunt mixing. So if you have voltage, output voltage, and if you connect this through a resistor, it becomes voltage shunt. If you want, you can verify the voltage shunt feedback circuit. Okay, another point is, yes, like this RE, take a RE here and take the connection from this to this. Suppose if the connection is like this, you connect a RE and yes, connect this point to this. Yes, what will happen? Actually, at the collector, you're going to get a 180 degrees phase shift output with respect to the input signal. But at emitter, you're going to get the same phased signal. Whatever the phase you are maintaining at Vs, you are going to get the same phase. So if you connect it like in the form of shunt, so what will happen? You are connecting a positive feedback, but ours is a negative feedback. But in the case of current series and voltage series, we didn't connect like this. We added that feedback in series. So what will happen? While adding in that series, yes, this voltage across RA gets subtracted from Vs. So it becomes negative. But here, if you connect the node from this to this, means if you want to add in terms of current to the input, then what will happen? You are adding a positive. You are adding a positive feedback. So that is not our concept. Our concept is negative feedback. That is the reason. Yes, we are using another transistor. See what will happen? Yes, here you are going to get 180 degrees phase shift. Fine. Yes, that 180 degrees phase shifted signal is given to the second transistor. Then, what is happening at this point? At this point, you are getting 360 degrees. Okay. But here what you are getting? As, yes, the input signal is 180 degrees. Here, you are going to get the same phase. Means I explained it here. So, you are going to get 180 degrees phase. Fine. So, now if you connect this point to this base, see here, you are connecting a 180 degrees phase at the input of your circuit. That is the reason your current shunt feedback amplifier consists of two transistors. Okay. So, with a single transistor circuit, it is not possible to connect current shunt feedback. Okay. What is the feedback component here? See here. Yes, this total is output of total circuit, and at this node, you connecting again into the input. So, your RE and R dash acts as feedback components. Fine. As next, V naught is equal to 0 is not making the feedback is equal to 0, because even though the output is 0, there is output current. So, there exists feedback. Hence, it is not at all voltage sampling. So, yes, this is current sampling because if you make I naught equal to 0, then automatically this drop becomes 0, means the feedback becomes 0. Okay, that is the reason it is current sampling. Then, why does shunt mixing? See here, connecting the feedback by using the node, not in terms of series, not like your voltage series or current series. Yes, like voltage shunt circuit, we are adding the feedback at this node. Node means there exists current division. Means you are adding the feedback in shunt with the externally applied signal. Shunt means current. Okay. Yes, that is the reason it is called current shunt feedback amplifier. Okay. So now I will explain the input and output circuit. Okay. First, I will explain the input circuit. Yes, what you have to do to find the input circuit? As this is current sampling, to draw the input circuit, you have to make I naught is equal to 0. Means you have to open the output loop. Yes, just open it. Means there is no current. Yes, you can remove. Totally you can remove. There is no current through RD. So now RA seems to be in series with R dash, and R dash other end is at base. Their series combination is grounded. Okay, then how to draw the input circuit? Another point here is, see here, this is II. What is II? IS minus IF. Means your feedback is subtracted from the externally applied current source. Where is that current IS? Yes, this is the current IS from Vs. Okay, to see only IS source, just apply source transformation. Yes, after the application of source transformation, the circuit becomes IS in parallel with RS. Okay, yes, now I'll draw the input circuit. RS, R dash and Rn. This is your input circuit. Yes. Now, I'll see about output circuit. I'll resume the connections. Yes. Now, to get the output circuit, what do you have to do? As this is shunt mixing, yes, you have to make Vs is equal to 0. Means, just short it. Simply short it. So, what will happen? Yes, this is also short. At this point, you have actually Vi1 because it is the Q1 input. It becomes 0. Yes, now if you see, yes, your Re and R dash are in parallel. Because for Re there is output current and R dash other end is at grounded. So, yes, it seems to be, take this node. This node is like this Re. And this is your R dash and it is grounded, and here a current is there, that is IE2. Okay. So now R dash and RE are seems to be parallel. Yes, R dash other end is at, yes, they say this is grounded. So instead of grounding here, we are grounding R dash other end here only. So what is the output circuit now? Yes, this is RD and this is R dash. Yes, these are grounded. And see, this is IF. Okay. Yes, R dash into the R dash, IF is there. Okay. So, yes, this other end is grounded. So, what is IF? This is your IF. Current flowing, yes, through R dash from the ground side is your IF. Fine. So, this is your output circuit. All other connections are same. Okay, now you can club to get your input and output circuit. And yes, I'm going to draw the input and output circuit. Yes, meanwhile, yes, the next step is H parameter model equivalent. So to draw that, you have to go for AC equivalent. For drawing AC equivalent, you have to make VCC is equal to 0. Yes, now when VCC is 0, RC1 and RC2 are grounded. Means from this collector RC1 is grounded and from this collector RC2 is grounded. Okay, just I am going to draw the input output circuit. Yes, just first you have to club these two, input and output circuit. Yes. This is RC1. This is RC2. And at emitter you have two things. One is your RE and other one is R dash. This current is your IF. This is your Q1 and this is your Q2. Fine. I'll indicate the terminals V1, C1, E1, V2, C2. Yes, this is the ground. So this is your input output circuit. Okay. So in the next video, I'll explain the H parameter model equivalent circuit and the analysis, means finding A, beta, Ri, R0, RIF, R0, etc. Okay, thank you very much. Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.